Hello, everybody, and welcome back. Today we are going to be going over Unit 3, Lesson Number 2, and today we're talking about carrying capacity. So you should have already downloaded your notes for today, and then this is the lesson that will correspond with those notes. So far we've talked about K versus R selected species, and we've talked about survivorship curves, so species that follow a type 1, a type 2, and a type 3 curve. Today we're going to move into talking about the way that populations can grow and then kind of what happens when they reach their limit. So we're going to go ahead and jump into this today, and again we're going to be focusing on the concept of carrying capacity. So population sizes are affected by different factors, and there's two different types of factors we need to know about. One is a density dependent and one is density independent. So a density dependent factor, if we think about what it means to be dependent on something, it means that this factor is going to be more or less detrimental depending on how many organisms are in the population. So the density is just how many organisms are a part of the population. So when density dependent factors, these influence an individual's probability of survival and reproduction in a manner that depends on the size of the population. So a factor or a density dependent factor could be something like food availability. So if there are more individuals in a population and food sources are scarce, that means that the organisms within the population are going to have to compete for the food sources, and the more organisms that are in the population, the more of a detrimental effect there will be to the overall numbers because they're competing for limited resources. On the other hand, a density independent factor is a factor that has the same effect on an individual's probability of survival and the amount of reproduction at any population size. These are things like a lot of times natural disturbances. So let's say there's a coastal species and a hurricane comes through and decimates a certain population. It doesn't matter how many organisms are in that population. The hurricane will come through and there's no way for the organisms to really compete their way out of that one, because it's a natural disaster that will come through and will decimate a population, whether there's 100 organisms or 5 in a certain population. So density dependent is impacted by how many individuals are in a population, and density independent is not. So we are going to be looking at growth curve models in this lesson, and there is going to be some math involved, but you guys will not have to do that much math on your own without me present. So anytime we have an independent asynchronous lesson, I really don't expect you guys to do that much math without me, at least having a video leading you through it. So the exponential growth model that we're going to talk about today is used to describe populations that continuously increase. So when we talk about a growth model, these are just the mathematical equations that can be used to predict population size at any moment in time. The growth rate of a population is the number of offspring an individual can produce in a given time period, minus the deaths of the individual or its offspring during the same period. So the growth rate is basically the birth minus the death rate. So if you have more births than you have deaths, your population will increase. If you have more deaths than you have births, then your population will decrease. The intrinsic growth rate is the maximum potential for growth of a population under ideal conditions with unlimited resources. So that is a perfect world. There's plenty of food, there's plenty of resources. That would be the ideal growth rate for a population. The exponential growth model is NT is equal to N naught times e to the RT. So this is just an equation that we can use to estimate a population's future size, so what the population will be at a point in time. So the future size will be the NT, and then the time will be, so that T value is just the amount of time that's passed, and then the R is going to be the intrinsic growth rate, and then the number of reproducing individuals currently in the population is that N naught. And then so anytime that you have an equation, this equation that you have to solve, you would be solving for one of these factors. So either the future size, the time it would take for it to get there, the intrinsic growth rate, or the number of individuals in the population. And anytime we're solving for any of those factors, the rest of them would be given to you in a problem. And then the J-shaped curve is just the curve of the exponential growth model when graphed, and we will take a look at this. So this is what the exponential growth model looks like. So when populations are not limited by resources, their growth can be very rapid. More bursts occur with each step in time, creating a J-shaped growth curve. So here we would see on our x-axis we have time, and on our y we have our population size. So as time increases, this is assuming this is a perfect world, there's no disturbances, there's plenty of access to resources. Over time, this population just keeps increasing and increasing exponentially. Okay, so we can imagine kind of, it's almost like doubling every so often. So the population will double and then double and then double and double again, and then it will just keep increasing and increasing. Now we know that there are going to be factors that will limit this. So this is not a model that necessarily all populations follow. This is just in a perfect world, the exponential growth that we would expect to see in any given population. So the logistical growth model describes populations that experience a carrying capacity. So this logistic growth model is going to be a little bit more realistic. So we know that there are limiting resources, which is a resource that populations can't live without, and that occur in quantities lower than the population would require to increase in size. So these are going to be the things like food resources, mineral resources, nutrient resources that are necessary in order to survive, that really determine the amount that a population can sustain because of their availability in the ecosystem. So because of these limiting resources, every population has a carrying capacity, and carrying capacity is represented by the letter K. So this is the limit of how many individuals in a population the environment can sustain. So we eventually get to a point where our ecosystems cannot support any more individuals in that particular population, and they reach their capacity, and so you would see kind of a drop off of the growth of those populations. So the logistic growth model is then a growth model that describes a population whose growth is initially exponential, but slows as the population approaches the carrying capacity of the environment. And the logistic growth model does create an S-shaped curve instead of a J-shaped. So your exponential growth model, and I just went back for a second, the exponential growth model is J-shaped. This is a perfect world. And then our logistic growth model is S-shaped, and this is more realistic because it shows carrying capacities. So this is what we mean by the S-shape. So this shows realistically what happens in populations when there are limiting resources, and we know that there are limiting resources in every single ecosystem. So we have our population starting to grow as time progresses. So the early growth is exponential because we don't have that many in our population and the resources are abundant. There's more resources than we do have organisms in our population. But as we begin to exponentially grow, well, we've got more organisms taking up those resources. There's more competition. There might be some disturbances. And so our growth begins to slow down. So our population growth begins to slow down. And this model can be used for any organism. So we can be talking about, dolphins, mosquitoes, humans, anything. So the growth begins to slow. And then eventually we will reach this dotted line up here. This is the carrying capacity. Okay. So this is the carrying capacity. This is the maximum amount of individuals in the population that can be supported by the ecosystem. So what happens is when the population gets to the carrying capacity, the growth rate will fall to zero. So the population will stop growing and it will kind of just cut off and maintain around its carrying capacity. And again, this is an S-shaped curve. And the difference between this and the exponential curve is that the exponential curve just keeps going. It's J-shaped. And then the logistic growth model cuts off at the carrying capacity. So it is S-shaped. So something about the logistic growth model, when we talked about our selected species in our last lesson, we talked about how a lot of times they will lay so many eggs and have so many offspring that they will overshoot their carrying capacity. And what that is when a population becomes larger than the environment's carrying capacity. So, they lay so many eggs at once, they can kind of overshoot that top portion. And what happens is when they overshoot it, they will experience something called a die-off. And that's just when there's a rapid decline in population due to deaths. So basically, if we were going to look at this, what would happen is let's say that we're looking at frogs. Okay, so the population size of frogs are growing. It's reaching its carrying capacity, and then all of a sudden, a bunch of frogs lay a bunch of eggs at once. Well, they overshoot their carrying capacity. So this line would come up, and what's happening is all those frogs would be existing above their carrying capacity. So there aren't enough resources to support those frogs. So their population might be up here, but then they're competing, there's not enough resources. So what we find is that the population will rapidly decline because there's not enough resources to support it. So it will go up and then it will fall back down, and most oftentimes it will come back way below the carrying capacity, and then the population will have to recover and then make its way back up to the carrying capacity before it stabilizes. Some organisms, especially like bugs, some bugs like cockroaches, will go through something called boom and bust cycles, where instead of really getting to a point where they will stabilize, they will overshoot, die off, overshoot, die off, overshoot, and then die off. And this is called boom and bust because they boom above their carrying capacity and they will bust and come down below it. But in a stable population, you will typically see where there's this exponential growth followed by this eventual stabilization at the carrying capacity. And an interesting thing about humans as well, since we do tie all of this course back to us and our impact, humans do a very good job, or so far we've done a very good job of raising our own carrying capacity. And we do that by lowering the carrying capacity of other organisms. Okay, so we can support, like, our carrying capacity. We haven't technically reached it yet because our population in the world is still growing. Our carrying capacity, right, is now above 7 billion, and we can continue to raise that capacity by lowering the capacity of other organisms. And what does that mean? That means that basically we can start using up so many resources. We, cut down forests and we cut down trees and we destroy habitats in order to build our houses. We use farmland for our crops, and we take from other organisms in order to give to ourselves, and we're able to support more humans, but at the cost of the earth not being able to support as many of other species. So that's just something to keep in mind. We do need to know that we as humans with technology can manipulate our own carrying capacity in ways that other organisms cannot. So that's all I have for you guys today. We will start looking at some math equations in our next lesson when we're together. But for now, we're just going to practice taking a look at these carrying capacity and these J versus S-shaped curves for our exponential and our logistical growth models. If you guys have any questions, let me know. And if not, I will see you guys in our next lesson.